Hello, welcome to this video. Today I'm going to be talking about Markov chains. So here's a tentative overview of what I'm going to be talking about. I'm going to be giving a brief explanation of the Markov chain. I'm going to be talking about the Markov property. I'm going to be talking about the idea of recursion and also linear algebra and the stationary distribution. And then finally, I'm going to be talking about something called the absorbing state. And I'll be tying all of these ideas into some examples as well. So here's a Markov chain explanation and motivation. A Markov chain is a mathematical model for systems that move step by step between different states where the future depends only on the present. So for example, weather forecasting, you could predict the probability of future weather, sun, rain, snow, based solely on the current day's weather state. Now that makes sense, right? If we're to predict a month out, our predictions might be a bit inaccurate and there's more uncertainty as we go out into the future. The present day to predict the following day is would be a lot more certain. Also, Google PageRank, modeling a user randomly clicking links on the web. The states are web pages, and the transition probabilities are links between them used to determine a page's importance. Now, we'll be talking about the idea of transition probabilities as well. Text and speech generation, modeling the sequence of words or phonemes. Early text generation systems used n-gram models, which are higher order Markov chains, to determine the likelihood of the next word given the preceding one. So these are fundamental ideas to large language models, right? So you're going to see the idea of Markov chains used in NLP, n-grams as mentioned, and also large language models. And then finally, like Monopoly, board games, also video games as well. We calculate the long-term probability stationary distribution of landing on specific squares based on dice rolls and game rules, okay? With video games, for example, it could be like where you get to a certain board and then you stay at that board for a long time, or most of the players, because it's too difficult to get past that particular level, right? We've all experienced that, those who have played video games, where you're just kind of stuck at this one level. And that would be the idea of a stationary distribution. And I'll be giving an example of a game later on. So I'm going to be talking about conditional probability, and this is pretty foundational to the idea of Markov chains. If you're interested, you could do a deeper dive into this topic in this video, probability and practical applications. And I have it out. Check out the video. So let's dive right in. Conditional probability and Markov property, how do they relate? So a Markov chain is a stochastic process that satisfies the Markov property. So we've got this pxt plus 1 is equal to x given like a history, right? The Markov property is basically saying that pxt plus 1 is equal to x is just dependent on xt, right? So xt plus 1 is just dependent on xt. And the probability of the next states depends on only the current state and not the full history that we just saw on the left-hand side. Okay, so that's important to note. That's what makes the Markov chain pretty special. So transition probabilities, we've got Pij is equal to Pxt plus 1 is equal to j, given xt is equal to I. We also have something called multi-step transition probabilities, right? So pxt plus 2 is equal to k given xt is equal to I, but we need some filler, right, to get from I to k, and that would be j, right? So we've got this pxt plus 2 is equal to k given xt plus 1 is equal to j times pxt plus 1 is equal to j given xt is equal to I, right? So that's connecting I to k. Okay, so that's a multi-step transition probability. So we could put conditional probabilities in matrix form, and these are called transition matrices. Now we've got P is equal to P11, P12, P21, and P22. That's a two-step transition matrix or a two-step Markov chain. Now, if we multiply those two, we get that two-step Markov chain, right? We could multiply P11 and P12 by P11 and P21. And then we could also multiply that by P12, P22. And we could also do that for the bottom row as well, right? So we multiply P21, P22 by P11, P21, and P12 and P22. And that is the law of total probability for each entry, right? That's what it follows. So we got that P11, P11 plus P12, P21. We've got that P12 position, P11 plus P12, P12 plus P12 times P22. And then we've got the following, P21 entry that does that, and then P22, okay? And that's the final matrix for P2, right? So that's a two-step transition matrix, two steps into the future. So let's give an example. There are two states, sunny and rainy. What is the probability that it's rainy 2 days from now, given today is sunny? So we've got t plus 2 is equal to rainy, right? Given that xt is equal to sunny, right? So that's 2 days ago, that's sunny. So we use that law of total probability again. We saw this earlier, where we need to kind of connect states, right? We need xt plus 1, okay, as the transition to xt plus 2, right? Given that it's xt, okay? So we decompose this, okay? So we got xt plus 2 is equal to rainy, given that xt plus 1 is equal to sunny, right? Times the probability of xt plus 1 equals to sunny, given xt is equal to sunny, plus the other possibility, xt plus 2 is equal to rainy, given xt plus 1 is equal to raining, times the probability of xt plus is equal to raining, given that it's sunny, okay? So there are two states, sunny and rainy. What is the probability that it's rainy 2 days from now, given today it's sunny? So we're going to use a transition matrix now. So we see these different states, right? Given sunny to sunny, sunny to rainy, rainy to sunny, rainy to rainy. And then we have this matrix. Now, 2 days from now, we would just multiply both of those matrices. Again, 0.8, 0.2 times 0.2 times 0.5, right? And we would do this across. The reason why we do this is okay, is because it's 2 days from now, right? So we're going to take the second entry, okay, 0.2 and 0.5. So here's the path one, sunny today to sunny tomorrow to rainy the day after, right? So we've got probability of xt plus 1 is equal to sunny, given xt is equal to sunny. And then we've got the probability of xt plus 2 is equal to rainy, given that xt plus 1 is equal to sunny. And then we've got path 2, right? We've got xt plus 1 is equal to rainy, given xt is equal to sunny, times probability of xt plus 2 is equal to rainy, given xt plus 1 is equal to rainy, right? So we're covering all the possibilities of what could be happening, okay? We have to make sure we have to kind of make sure that we're understanding the problem, right? Given today is sunny, so we know from there that basically xt is going to be equal to s. We don't know what xt plus 1 is going to be equal to, right? Because it could be either sunny or rainy, right? And then we're looking for the xt plus 2 is equal to rainy, right? Given that xt plus 1 could equal to be xt plus 1 could be equal to sunny or rainy. That's what we don't know. So we would just multiply that out, and we get 0.74, 0.65, 0.26, 0.35. Now let's talk about recursion and Markov chains. We know that pi t plus 1 is equal to pi t times p, okay? And the distribution at the next step is defined using the current step, and you repeat that same rule again and again. Now here's a recursion example. There are two states, sunny and rainy. We've got this matrix, P. Interpretation, if today is sunny, tomorrow is sunny, which is 0.8. It could be cloudy, which is 0.2. If today is cloudy, tomorrow is sunny, 0.4, or cloudy, 0.6. Okay, that could be, I'm sorry for the typo, it's rainy, okay? So pi t is equal to pi t s, the condition that it's sunny, pi t is equal to c, which is cloudy or rainy. And pi t plus 1 is equal to pi t times p. So for example, if today's distribution is pi naught is equal to 1, 0, we will compute tomorrow by multiplying it by that particular transition matrix, and we get 0.8, 0.2. If we were to compute the day after tomorrow, we would do the following. 0.8 times 0.2, what we found as pi 1, we multiply that by the transition matrix, and then we get 0.72 and 0.28. So recursion lets us compute the distribution step by step using the previous day's probabilities. The general formula, again, is pi t. I apologize. The general formula is pi t times p, what we saw earlier, okay? So let's move on to linear algebra and stationary distribution. So we're going to use an example. A website has two states. State A, user is on the home page. State B, user is on the product page. At each click, 80% stay on the same page, while 20% switch pages. We construct the transition matrix and find the stationary distribution. You'd write 0.8, 0.2, 0.2, 0.8, then solve for the stationary distribution. Now we use that idea of recursion that we saw earlier, right? Pi is equal to p times pi. And then we restrict that pi is equal to 1. Okay, so the distribution has to be somewhat of a fraction, okay? 0.2, 0.8, 0.5, 0.5, whatnot, okay? So we've got this transition matrix. we use a characteristic polynomial, okay, which is this formula, determinant p times minus lambda I. We subtract the diagonals, the lambda from the diagonal entries, right? And then we multiply that out, right? So we multiply 0.8 minus lambda times 0.8 minus lambda minus 0.4, or minus 0.2 squared. So we get this, and then we set it to, it ends up becoming lambda squared minus 1.6 lambda plus 0.6. We set that equal to 0. We use this calculus rule, negative b plus or minus b squared minus 4ac over 2a. Lambda is equal to 1.6 plus minus 0.4 divided by 2. We get for lambda 1 is 1, right? Because we've got two of these that we have to solve for, lambda 1, right? And then we get lambda 2 is equal to 0.6. Here's the thing though. From this, we only use the lambda is equal to 1. Because only eigenvalue 1 produces a distribution that persists unchanged forever. Remember the stationary distribution, the idea is we want to find a long run equilibrium, okay? If we have it at 0.6, excuse me, so this is the distribution that remains unchanged, right? We've got that 1 times pi, okay? And I was a little bit ahead of myself earlier, so I apologize. But here's the reason why 0.6n will go to 0, okay? And here's a little bit of the algebra that leads to that, right? So lambda to the k will go to 0 as k goes to infinity, okay? So the stationary distribution is a long-run equilibrium distribution, and we want it to persist. Okay, so that's the characteristic of it. That's the reason why we would pick the lambda is equal to 1, okay, versus 0.6. So we do that, we minus the 1, we found out what the lambda was, we get the following transition matrix. We try to solve for a system of linear equations, right? X, y is equal to 0, 0. We do some algebra, x is equal to y. Take v is equal to 1, 1 as the eigenvector. Pi is equal to 1 over v plus 1 plus v2, v1, v2. The stationary distribution is 1/2, 1/2, okay? And again, the stationary distribution is the long-run equilibrium of a Markov chain. The probabilities the system settle into after many transitions, regardless of where it started, okay? If we had that lambda at 0.6, there will be no transition, right? Because it'll go to 0. So let's quickly talk about an absorbing state. An absorbing state in a Markov chain is a state that once entered cannot be left. Formally, its self-transition probability is 1, meaning the process remains in that state forever after reaching it. I'm going to give you an example with like a simple video game, okay? So we got a player, level 1, okay? But in this level, something could happen, right? It's possible that he loses, the game is over. That would be considered an absorbing state. But he could do well as well, right? So he could get past to level 2, and he could win the game, right? This is a 2-level game. If you get past level 1, you win level 2, you win the game, okay? It's really simple. That would also be considered an absorbing state. Okay. Now let's give an absorbing state example with a game, and I'm going to be simulating like a very simple game, right? We've got a village, forest, mountain as boards, and then G is game over. Okay, so a person's traveling through a village, forest, mountain. Very simplified idea. It's not like Legend of Zelda or some complex game, but it's just you're going through these three stages, and then finally there's a game over stage. Okay, and we could represent that as VFMG. And of course, we've got this transition matrix, right? Where we have from V to V, V to F is 0.7, V to M is 0.3, and so forth, right? So these entries we're going from board to board, okay? Or you could just stay in the same board, right? V to V. You've got F to M, F to G, which is 1.0, which is an absorbing state, where it's game over. We've got G to G, which is definitely game over, right? Which is 1.0. That's an absorbing state, okay? And again, absorbing state is a state from which it is impossible to leave. Once the system enters into the state, it remains there forever. So here's an example how we could express that particular transition matrix in a graph. And I think it's very useful to do this. Um, it helps you kind of see what's exactly happening. So we got the village to the forest 0.7, village to mountain 0.3, mountain to forest 0.4. Forest is a game over once you get into the forest, right? That's an absorbing state, right? And then game over is obviously an absorbing state as well. So you kind of see the the rows of the matrix translated into a graph, and that's very, very helpful. So let's continue our example with the game. If you start from the village, right, from V to F, we get 0.7, right? The chain is not absorbed, by the way. Or yeah, it is absorbed. I apologize, right? Because if you go to V to F, it's 0.7, but F is an absorbing state, right? V to M with probability 0.3, then M to F is 0.4, and M to G is 0.6. So we use that law of total probability. End in F given V is 0.7 plus 0.3 times 0.4, which is 0.82. End in G given V is 0.3 times 0.6, and that's 0.18. And we get the distribution 0.82, 0.18. If we do that, P end in F given M is 0.4. And then end in G given M is 0.6. We get 0.4 and 0.6. Okay. So here's an example where there's only one absorbing state, right? We see that D is an absorbing state with one. Previous example, we had two. And this is the way we would write it. Meaning that 0% long run probability in A, 0% in B, 0% in C, and 100% in D, right? We won the game or we lost the game. We're basically out. So 100% in D. Okay, so that's what happens. So that's it for now. Thanks for tuning in, and I hope you have a great day.